Good morning to one and all present here. A is the first of the alphabet. God is the primary source and force of the world. Above lines are well known as Agara Mudala Eduthellam Adi Bhagavan Mudache Ulagu. Means that everything begins with God. Let's invoke God's presence and His blessings with prayer song by our department choir, followed by prayer by Dr. S. Janet Priscilla, Assistant Professor, Department of Physics. Let's all rise up and remain standing for both the prayer song and prayer.
Heavenly Father, we come to thy presence in the name of Lord and Savior Jesus Christ. Lord, we thank you for this 13th KMK Endowment Lecture. We thank you for the wisdom and foresight of our alumni who has invested in the pursuit of knowledge and understanding. Lord, may this lecture be a source of inspiration, enlightenment, and challenge. We thank you for the special speaker of the day. May his words be filled with your wisdom and guided by your truth. Grant him eloquence of expression that his message may resonate deeply in our minds. We pray for all our students and faculty members. May we all listen to the lecture with open mind. May this lecture be a catalyst for new ideas, new discoveries, and a renewed commitment to the pursuit of excellence. We ask this in the mighty and the matchless name of our Lord and Savior Jesus Christ. Amen.
Thank you, Dr. S. Janet Priscilla, for the prayer and the department choir for the prayer song. Now I request the dignitaries to occupy the dais. So I request the dignitaries to occupy the dais. Now I invite Dr. Johanna Christian Bresana, Assistant Associate Professor, Executive Committee Member, Physics Alumni Society, Department of Physics, to welcome the gathering.
Good morning, ladies and gentlemen. It's a privilege for me to welcome everyone of you for this 13th edition of Dr. K.M. Karunakaran Endowment Lecture. Dr. K.M.K. served in the department for more than 2.5 decades, and he was specialized in classical and quantum mechanics, a very fantastic teacher. And I'm one of his students, but I didn't have the privilege of attending his classes, but whenever I had any doubts in classical or in quantum mechanics, we used to approach, and then he used to explain in a crystal clear method of how to solve a classical problem or quantum mechanical problem. Such a great teacher. And it's a fitting that we celebrate, we instituted this endowment lecture, and it is the 13th edition, and it has got a global recognition today. So at this point of time, I welcome Dr. Claudio Ferrari, Director of Research, Institute of Materials for Electronics and Magnetism, National Research Council. So thank you very much for accepting our invitation, and we heartily welcome you for this 13th edition. Thank you, sir. Dr. Stephen was well known to us, and he's a great scientist. He's one of the top 2% of the scientists by Stanford University. And it is a great honor to have you with us, sir. Welcome you for this 13th edition, sir. Thank you. He is also the head of the Department of Material Science, University of Madras. Dr. Balaji, sir, welcome you for joining us for this function. Thank you, sir. Nothing would have been possible with our fantastic head of the department. And I think during his first period, this program was instituted, if I remember right. He's the person who started this endowment lecture, contacting the family, contacting the various alumni, and he took a lot of steps to make it possible. We had a lot of struggle initially in 2011 to institute this, but somehow because of his tireless effort, we are able to institute this. And during the pandemic also we had a lot of struggle, but he was able to conduct this program successfully. And he has taken this to a global level by today's program. So it is also fitting to thank him and also welcome him for this function. And this might be his last inaugural function talk of the endowment lecture. Thank you, Dr. Sam. And physics department is the youngest department in the college, in terms of the faculty members. Such a vibrant department, and anything that you give it to them, it is made possible. So at this point of time, I welcome the Department of Physics faculty members for this program, and nothing would have been possible without your tireless effort. Thank you. And the lab attenders and the other support staff also I welcome, and I think they will be joining us. Nothing is possible without you guys, because the department is existing for you, and the department exists because of the students, not the staff. So students play a major role in every little aspect of the department. And this is the, though their work are not seen too much, but every single step in the program is done by the students. And it is really fitting to welcome each and every one of you for this 13th edition of Dr. KMK lecture, which is made global. So welcome each one of you for this function, and I once again welcome every one of you for this 13th edition of Dr. KM Karunakaran lecture. Thank you and welcome all of you.
Thank you, sir. I invite Dr. P. Samuel Asirvadam, Associate Professor and Head, Department of Physics, Vice President, Physics Alumni Society, to give insight about Professor K.M. Karunakaran Endowment Lecture and Physics Alumni Society.
Very good morning to each and every one of you. Very special word of welcome to Dr. Claudio Ferrari, Dr. Stephen, Dr. Balaji, and all my colleagues and students. And a special word of welcome to the executive committee members of the Physics Alumni Society, including Rebecca. Right. I'll just give a glimpse of who is Dr. Professor K.M. Karunakaran and why we celebrate his legacy in MCC. So, Professor K.M. Karunakaran served the department from 1950, and prior to that he did his took his honors degree from the department as well as MA from the crystallography department of University of Madras, and then he took his PhD from the University of Kansas in USA. and he served as the head of the department for a long period of time. He was one of the longest serving head, and he retired from the department in the year 1987. That was the year when I graduated for my PG, and I joined in his place in 1987 as a staff. So Professor K. Karunakaran was known as a very good teacher. He has taught me quantum mechanics. At that time he was not well, he was quite sick, but he used to use only OHP sheets and he used to write it on that. That is sitting, and he used to write on it and then project it. He was a very good teacher of quantum mechanics. He can just teach it without any paper or anything. I still remember one of the topics he taught me. That was Einstein's A and B coefficients. That is quantum optics. That's the area. So he was a very good teacher. As I specified here, he was acknowledged as one of the best, if not the best, the very best in the University of Madras circle. Because those days, University of Madras had their PG classes in either all students of Pachapas College, Presidency College and MCC. They had common classes, either in the university or in Pachapas and at MCC or in Presidency. They will move. Those teachers will take classes, or those students will come to Chennai, Tambaram for their classes. So those days, only 3 colleges had PG physics, and these students will go for their lectures to other colleges that will be taught only there. So like that, in the Madras University circle, he was known as one of the best teacher of quantum mechanics in those years. So that is one thing. And Professor B.M. Arthur, who was a senior teacher who is still alive, he's around 97 years. That's what he said about Professor KMK. For Professor K.M. Karunakaran, every lecture was a performance. For any performance, we'll make such a preparation. And he took all classes only with preparation. And it was quite good class. Okay, I'm the only person who has attended this class here. Then the students of his students, not only his students, MCC students, alumni decided to create an endowment in his name so that we can have a lecture every year. And prior to that, there's already an existing Professor KMK prizes already there. So this scholarship was, this endowment was instituted during the headship of Dr. Philomen Raj, and one of the main person who was behind this was Dr. M. Lakshminarayan, our president of the Physics Alumni Society, and he is the one. He is unable to come today. It was very much, and quite a lot of other people. So by the contribution of all his students, some faculty and others, this endowment was created. So we are happy. This is the 13th edition of Professor KMK lecture, and we are very, very happy to have a person like Dr. Claudio Ferrari to be here to give this lecture. So I'll give some more glimpses of the papers by Professor KMK. One is in Journal of Chemical Physics, the first one. Then the other 2 are Indian Journal of Quantum Chemistry in the earlier years, somewhere around 1970s. And his guide, Ralph E. Christopherson, later he became the president of Colorado University. I'm talking about this guide. Guide of Professor KMK was a very big shot. He was also the CEO of several companies like SmithKline Beecham and several other companies later. If you Google Ralph E. Christopherson, you will go there. There's a book written by Christopherson, which I'll mention. Prior to that, this is Dr. K.M. Karunakaran was an elected member of the American Physical Society in the year 1968, when he was in the University of Kansas as a student, but it was quite, that's one. I'll have only two or three more slides. This is a book written by Professor Christopherson, Basic Principles and Techniques of Molecular Quantum Mechanics. It's a very good book, published in the year 1989, in which he acknowledges Dr. K.M. Karunakaran as a student. So that is some excerpts from the book. I'll just give a glimpse of the 13 lectures that has been already conducted. The first lecture, okay, these are the Professor K. Tyagarajan of IIT Delhi. Then of the 13 lectures, 6 were given by students, alumni of MCC. Second one was by Professor N. Gautam, who was an alumni. Then Dr. C.S. Sundar from IGCAR. Then Professor Sundar Ram Prabhu of IIT Madras is an alumni, classmate of Dr. N. Then Professor Dr. Lakshmanan from Bharatdasan University, he is also an alumni of MCC. Then Professor Dr. Gurubaran of the Indian Institute of Geomagnetism, he was my classmate in MCC. Then Professor Dr. V. Balakrishnan of IIT Madras. Then Professor Lakshmi Bala of IIT Madras. Then during COVID time, we had this lecture in the year 2021 by Padma Shri Professor H.C. Verma, whose book on concepts of physics is quite well known among students. Then we had Dr. Aruna Dattatreya and Dr. V. Subramanian. Both of them are NCCNs. Then we had Dr. S. Gunasekharan last year, and currently the present lecture today we have by Dr. Claudio Ferrari. He is the director of the IMEA, not senior researcher. He is from 2023, he is the director of that institute. I want to mention that specifically because I prepared this bit earlier. I came to know about that detail only yesterday. Okay, so this is about the Professor KMK and the genesis of the KMK lecture. So thank you, and I'm sure that the lecture will be quite beneficial. Thank you.
Thank you, sir. May I now invite Dr. P. Subhashini, Associate Professor, Department of Physics, to introduce the distinguished
distinguished guest of the day, dignitaries, respected head of the department, dear faculty, alumni and students. With an energetic morning wishes, I consider myself privileged to introduce the eminent speaker of the day. Ladies and gentlemen, you are witnessing on the chair Dr. Claudio Ferrari, Director of Research, Institute of Materials for Electronics and Magnetism, IMEM, which is a part of the National Research Council, Parma, Italy. It is interesting to know that Sir, after graduation in physics, has started as an officer in the Italian Army at the Military Geographical Institute. He then became the vice major in the town of Colombo, responsible of city planning and environment. He then became the senior researcher at IMEM, and now he rose to be the director of research at Institute of Materials for Electronic and Magnetism, IMEM, from 2023 onwards. Research proficiency. Dr. Claudio Ferrari has authored 6 book chapters and more than 220 papers published in international ISI journals with international referees, and we may note that its Sir's H index is 33, and Sir has provided 20 invited lectures at international congresses. Since 2005, Dr. Ferrari's investigation areas of research includes materials and devices for photovoltaic energy, particularly in the field of micro cogeneration, thermophotovoltaic micro cogenerators, low bandgap photovoltaic cells, and selective emitters for thermophotovoltaics. Research projects. Dear students, please notice the great numbers on the presentation. 668 kilo euros. In Indian rupees, it is over 6 crores. 400k euros. It is over 3.6 crores. The least I found on his project was 20k euros, which is over 18 lakhs. The amounts are proportionate to the weightage of indispensable contributions of Sir in projects such as portable sensors for unmanned explosive detection, increase in the technological readiness level for the realization of hard X-rays, soft gamma ray level optics, new technologies for the energy efficiency and use of the renewable resources, growth and characterization of luminescent materials and devices for optoelectronic and thermophotovoltaic applications, and many more. You can see Sir's collaborations and the institutes and the level of projects that Sir has undertaken. Owing to the want of time, I have mentioned only few here. And for the audience, who wants to know about IMEM? IMEM develops interdisciplinary research approaches in the field of material science, which include advanced methods of synthesis and characterization of materials, as well as device manufacturing technologies designed with the aim of exploring and demonstrating the functional properties of materials themselves. Main research activities of IMEM are materials and technologies for green energy, sensors for IoT and sustainable development, smart and neuromorphic biointerfacing systems, magnetica and multiferroid materials, and many more. All these are hot topics of research. Also, IMEM's effort to train new researchers is noteworthy, mainly through the participation in the Materials Science and Technology PhD program of the Parma University. After witnessing the CV of Dr. Claudio and his many projects fastened around sensors, it is crystal clear that Dr. Claudio Ferrari is the appropriate person to enlighten us and address on sensors for security, especially for the young minds present here waiting to hone their skills. Signore, siamo onorati. In Italian, this means, Sir, we are honored. Yes, sir, we are honored by your presence today. I thank everyone for the opportunity given to me.
Thank you, ma'am. So on behalf of our department and Physics Alumni Society, I invite our head of the department, Dr. P. Samuel Asirvadam, to felicitate the chief guest and speaker for the day with department memento. And a memento to remember India and Madras Christian College. Thank you, sir. A few words regarding the memento. The engraving of elephants was done using woods of different types. Elephants are considered as the epitome of wisdom, wealth, and strength in India. They are famed for their high intelligence and exceptional memory. Hope this memento will always bring back the memories of your visit to India. On behalf of our department and Physics Alumni Society, I request our head of department to present a gift to Dr. A. Stephen, Professor and Head, Department of Material Science, University of Madras. Thank you, sir. Moving on to the fulcrum of the program, now I invite our beloved speaker for the day to deliver the talk on sensors for security.
First of all, I want to thank you for inviting me to have such a possibility. And thank you, Professor Stephen, for such a possibility. And thank you to all of you because so many numerous people here that I did not expect. I hope to give you a pleasant lecture and give you a way of understanding that may be interesting for you. First of all, I will present my institute. The institute is IMEM, means Institute for Material for Electronic and Magnetism. It was founded nearly 50 years ago. We are in Parma. Parma, it is a part of a campus, a university campus, and our institute is one building among the others of the campus. Can I go? Okay. Okay, this is the scheme of our institute. We have several departments doing research with magnetic and electronic materials. And this is the entrance of the institute. Okay, just enough. Parma is a historical town, as many others in Italy. It's an average size town of approximately 200,000 inhabitants. You know that Italy is a very ancient culture and civilization. Parma, as many other towns in Italy, were founded by Romans more than 2,000 years ago. And there are many historical things. So I can move to the presentation. It's enough for this. Can you? Okay. Sensor for security. This was a part of a research that was performed by a NATO program that I will mention you before. And the work was done by me and my colleagues of the Institute, ISAN, and also colleagues from the chemistry department that were involved in the preparation of the sensors. So I'm able to move to the next slide alone, or somebody? Okay. So the outline of my talk, I will give you a small introduction, why we need a sensor for gas sensor for security. This sensor that I propose are based on a field effect transistor made of on nanowires. I will give you information about the way of in which we grow germanium nanowires, structural characterization, contact preparation, electrical measurements, and test functionalization. Okay. So, why we are using semiconducting nanowires to make a sensor? The reason is that for nanostructures, the ratio between surface and volume is very high. So it is much easier to prepare devices which are very sensitive to the ambient, very sensitive to the presence of gases. The sensitivity is much higher with respect to bulk material, of course. And it was demonstrated that semiconducting nanowires can be able to detect gases to the detection limit to 10 to the minus 6 part per trillion, so a very high sensitivity. You can distinguish a molecule among billions of others. And in the present study, we will focus our attention to the detection of a molecule of a common explosive, trinitrotoluene, by functionalization of germanium nanowires. Why trinitrotoluene? Trinitrotoluene is the most is a modern explosive, is the most common explosive which is used in military devices, but also for improvised explosive devices that are used by terrorists. They are used because it's extremely easy to prepare such a device. They are very dangerous, and you can find relatively easy trinitrotoluene. Many of the other modern explosives are very similar or based on trinitrotoluene. I must mention that trinitrotoluene is absolutely safe to be handled. I had to make a course about explosives during my research, and I can say that you can treat trinitrotoluene in any way. You can press, you can beat, you can burn. It doesn't explode at all. So it is very safe material. From this point of view, we could make our research without any doubt. It is important to detect such explosive, for instance, for landmines. You know that the problem of landmines which are buried is very, very severe. For instance, I can tell you that still now in Egypt, they are discovering landmines which were buried during the Second World War. That means 8 years ago. They're still there and still working, so very dangerous. And in many other places in the world, the situation is even worse. I can mention Ukraine now, but also Azerbaijan. Recently, they covered the land by such landmines, and to discover them is extremely dangerous and very difficult and expensive. So to find a way to detect such landmines is very, very important for many, for humanitarian purposes and also for economic purposes. The base of our device is functionalized semiconducting nanowires. And this is, I will demonstrate that is a viable approach to realize detector with a high sensitivity and reduce electrical consumption. Because at the beginning of our project, the idea was to fit the device on drones. And drones can be moved in the rooms, can be moved in the surroundings in a very safe way without exposing humans to danger. This would be extremely interesting. So, okay. We are speaking about gas detection. But in fact, trinitrotoluene is a solid material. So why we are able to detect trinitrotoluene by gas? It's because of the smell. Trinitrotoluene, as any other solid substance, has a particular smell that can be detected by dogs, but not by humans. So our purpose is to mimic the nose of the dogs to be able to detect in a safe way the presence of trinitrotoluene. Here you can see this is true for any solid material in equilibrium at a given temperature. There is a pressure, a partial pressure of the molecule of the solid in air, and such a partial pressure changes very rapidly with temperature. Approximately here, at room temperature, we have a vapor pressure of approximately 10 to the minus 8 torr, which corresponds to the 10 to the minus 8 atmosphere. The physical meaning is that every trillion of air molecules, there are 10 molecules of trinitrotoluene. And to produce a sensor able to detect means to be able to distinguish among 10 to the 8th molecule. This is why it's a very difficult task. So, the base of our device is the nanowire field effect transistor. A field effect transistor is made by source, drain, contact, and a gate electrode. This is a nanowires-based field effect transistor which was performed years ago based on silicon. In that case, the gate is provided by the contact on the substrate. By modifying and by applying potential to this gate, you can modulate the current flowing from source to drain. It is very sensitive to the potential that you apply here, and practically there is no current between the gate and the other electrodes. That's why it's very do not require very high power to work. In our case, we will not have a gate made based on the substrate, but the gate will be the ambient. The gate will be the surrounding of the nanowire that will be sensitive to the gas to be detected. Another problem is that you need a proper doping of such semiconducting material in order to have proper conductivity of the material. A suitable doping for having an effective field effect transistor is around 10 to the 17 carriers per cubic centimeter. And it is shown in literature that in several cases such doping is do not need to be intentionally introduced, but is spontaneous doping due to the preparation technique. Okay, so we use germanium as a starting semiconducting material for several reasons. The most common semiconducting material, you know, is silicon. But in the case of germanium, we have some advantages. First of all, the band gap is smaller than silicon. There is a higher carrier mobility with respect to silicon. Larger bore radius. It is the confinement effect, quantum confinement effect, is much stronger in the case of germanium with respect to silicon. And first of all, from the technical point of view, we do not hit high deposition temperature. So in the lab it is easy to reproduce and to have a proper growth technique. In our case, we use a metal organic vapor phase epitaxy reactor with a growth temperature. You see a very relatively low growth temperature. It is 370 460 degrees. Partial pressure 100 millibar, and we use hydrogen as a carrier gas. Another important issue that could be faced is the danger, because the standard precursor for, you know that the MOCVD growth, there is a gas flowing into the chamber, then cracks and deposit, in that case, germanium. A standard precursor is germane, which is toxic, flammable, and explosive, and also need a higher growth temperature. And we use a relatively new source, which is isobutyl germane, which is a liquid metal organic with a low cracking temperature and can be much more easily managed in a research environment. This is important for our research. So, how to grow the germanium nanowires? A classical method to prepare germanium nanowire is to start from a gold droplet, gold nanoparticles that can be deposited on a substrate, and because of particular behavior of germanium in presence of gold, with a given temperature, the germanium atoms are absorbed by the gold droplets and start to deposit between the droplet and the substrate. And in this way, you obtain nanowires that have the same size as the droplet. So by choosing proper size of a gold nanoparticle, you can also determine the diameter of the germanium nanowires. These are the first experimental results that we were obtained by our growth technique. These are the germanium nanowires seen by electron microscope. You see the marker here. The nanowires, you can obtain nanowires very, very long, with between 15 to 30 meter long nanowires. And also the diameter of the nanowires were almost constant with minimal tapering. So this diameter is practically constant from the beginning to the end. These are also scanning electron microscope pictures of the first results of the growth. There are short nanowires which are attached to the substrate. In that case, we use a silicon 111 substrate material. And what you can see is that nanowires are grown mainly on 111 direction of the substrate. They continue the lattice of the substrate along the 111 direction. The result was confirmed both by transmission electron microscope and by X-ray diffraction. You can see that the 111 direction with respect to the 100 surface of the lattice are inclined by 60 degrees with respect to the surface. And this is a transmission electron micrograph of a typical germanium nanowire. Maybe you can see from your side that the very regular lattice, I don't know if it's possible to see in the picture, very regular lattice, and the direction of the nanowire is 111 crystallographic direction. And this is a diffraction pattern obtained by transmission electron microscope that shows that it is a very regular lattice with the presence of many diffraction spots in the picture. So it is demonstrated that the germanium nanowire are made of a very perfect lattice grown along 111 direction. Okay, this is another details of germanium nanowires near the gold droplets. So, just to remind you, the germanium starts to grow at the interface between the gold droplets and the substrate, and continue to grow at the contact of the gold droplets. So at the end you have such nanowires with a gold droplet on the tip, and which start from the substrate. And you can see that the lattice is, there is also crystalline gold tip when the temperature is decreased, and behind the nanowire, which has the same size as the gold droplet, this is a nearly perfect germanium lattice. So the result was, from this point, very good. Another critical point, if you want to prepare a field effect transistor based on a single nanowire, is that you have to remove the nanowires from the substrate. This was not an easy task, but I can tell you the way. So we start from a substrate containing nanowires, we, by using ultrasonication, putting the sample in an ultrasonicator, then the final result, we have a suspension of nanowires in a liquid medium. So we were successful in such a way of removing nanowire. Of course, one must properly apply such a method in order not to destroy too much nanowire, because if you continue to apply ultrasonication, then nanowires break and then are not suitable for the preparation. So the way of preparing our field effect transistor based on a single nanowires is relatively simple. We start from the liquid containing the nanowires. We put droplets of such liquid on a substrate with electrodes proposed, and of course we have a random deposition of nanowires, but only a few of them are suitable for obtaining the final device, which is based on a single nanowires. It's a very random process, very low yield, so we use many thousands, billions of nanowires, and maybe we have 2 or 3 suitable devices. We couldn't find a better way to do that, because in principle you should handle a single nanowire, put in the proper position, and make contact. But at the end, we were successful in finding a proper nanowire. I show here 2 examples of the device that we could obtain. We have here the contacts that have a low micrometer spacing, so also the contacts are not so easy to be prepared. We found nanowires in which the ends of the nanowire is not too far from the gold contacts here, and we realized by using focused ion beam techniques the contacts between the ends of the nanowires and the gold contacts. And this is an example in which the original nanowire is not directly in contact with the gold contact. Another example is here, in which we found, fortunately, a single germanium nanowires in which the ends go on gold electrode. In any case, even if the ends go to the gold electrodes, this is not enough to prepare the device, and we need to prepare proper contacts. And for this, we use the focused ion beam technique that we have in our facility, in our institute. How this facility works? It is, in principle, simple, not so much simple. The focused ion beam system is essentially made by a scanning electron microscope and a focused ion beam in which a platinum precursor is focused on the sample surface. When the platinum precursor goes on the surface of the sample, by moving the electron beam, then there is a cracking of the platinum precursors, and a platinum contact is deposited. In such a way, we can prepare nanostructured device based on platinum contact. These are the first electrical characterization of our devices, and the results were quite encouraging. At the end, we with several 10 micrometer long nanowires, we could measure. You see that the current as a function of voltage, EV characteristic, is very linear in a relatively large range of applied voltage, so that means as an ohmic behavior, very ohmic behavior. The resistance was of the order of 10 to 6 ohm, and we could find, considering the nanowire length and nanowire diameter, the resistivity of the material of the order of 0.19 ohm per centimeter. And this was true for several nanowires which were grown in different runs. So we have more or less a constant electrical property of the material. So at the end, we could detect a perfect ohmic behavior and an excellent contact quality, because the dependence is very, very linear in a relatively large range. And the constant resistivity of germanium is almost independent on the range. So, since we have the resistivity of the material, we could have an idea of the carrier concentration and the doping of the material. This is a result of a very old paper that reports the resistivity of the material as a function of impurity concentration, both for N-type conductivity and for P-type conductivity. The difference is not very large. Considering that we have a resistivity in the order of 0.1, 0.2 ohm per centimeter, so approximately this level, we conclude that we should have an impurity concentration of the order of 10 to the 16, 10 to 18 to 10 to the 17. An intentional impurity concentration. We don't know exactly the origin of such concentration, but we found that at the end it is suitable for our device. These are other examples of our other results that we obtained by the deposition. You know that the deposition of nanowire is totally random. So in some cases we have single nanowire, but in many, many other cases we have a network of such nanowires, and this is the results. And in principle also the network can be used for detecting the nanowire. These are, for instance, the results of resistivity determined in a single nanowire and network of germanium nanowire. The current is much higher in the case of contact network. This is the current in this case of single nanowire. If there is no contact, the resistivity is very high and the current is very low. So, at the end, we need to prepare a sensor for a gas. We are just at the beginning of our process because we were able to grow the nanowires and to contact them. How to prepare a sensor? Of course, we need something to make it sensitive to the gas that we want to detect. And this is called functionalization, to make it sensitive for gas. And which is the property of trinitro-toluene molecule that can be used for the detector. The fact that this is the molecule of the trinitro-toluene, which is aromatic ring with the 3 anode NH2 bindings, and because of this nitrogen dioxide binding, electrons are removed from the center of the ring and move to the nitrogen dioxide part of the molecule, and this creates a very electron-poor aromatic ring. So this is attracting electrons from outside, from the ambient. So we should use a molecule which is electron-rich and can form a weak bond with such a molecule. And the typical molecule that can be used for such a purpose is the amino group. So we have other molecules. If we are able to put amino groups on the surface of our nanowires, then TNT molecules will be attracted by our functionalized nanowires. This is a possible example of functionalization with the thiol-based. So, what happens when you have TNT binding? So that means the amino group is attracted by trimethyltoluene molecule. There is acid-base pair interaction, charge transfer between NH2 molecule to the trimethyltoluene molecule. It means charge transfer, an electrical field is generated in the vicinity of nanowire surface, and such electrical field can affect the nanowire conductivity. So once we are able to functionalize our nanowire with such NH2 amino group, then we will be able to realize such a sensor for TNT. It is interesting to observe that even different explosives, which are not exactly like a TNT but have more or less a similar structure, may behave in the same way. So in principle, this sensor can be used for many different explosives. Okay, so the method that we use to functionalize our nanowires is try to attach such thiol-based compounds on the surface of the nanowires. To do that, you must keep in mind that germanium nanowire as well as silicon-based material are always oxidized. When you remove from the grow chamber, in a few minutes a thin oxide layer is formed, which affects very much the property of the material. So in order to functionalize germanium nanowire, the first step is to completely remove the oxide at the surface of the nanowire, and this was done in our case by using fluoridic acid, diluted fluoridic acid, that removed completely oxide, and hydrogen bonds are formed at the surface of the nanowires. Another possible way is using diluted chloride, hydrogen chloride, and this removes germanium oxide, and then applied such a thiol-based molecules. We expect that such bindings are formed that terminate with amino group, and this should be a suitable functionalization of the material. The problem is that the step in functionalization, we see that for our scanning electron microscope, the nanowire are still attached on the substrate before sonication, of course, and by using a scanning electron microscope, it is very difficult to see the thin layer of germanium oxide, even by use transmission electron microscope. But we are sure that the germanium oxide is present. So the first step is to remove the germanium oxide. Another critical point is that how can you verify that the functionalization was successful? Because we should detect molecules at the surface of the nanowires that cannot be easily seen by any microscopic technique, not by scanning electron microscope. We, in our case, we tried such ethyol compound, and in order to functionalize it, the process was quite long. We kept it at 80 degrees for 5 days with a high concentration of octanethiol material. And we expect that the final result is something like that. We have sulfur atoms in contact with the germanium nanowire, then a chain of octanethiol, and at the end the amino groups at the surface. How can we be sure that the functionalization process worked? We couldn't easily find a technique to demonstrate that the functionalization was working. We tried Raman, infrared spectroscopy, but that in principle should be sensitive to such material, but we didn't find any signal demonstrating the presence of molecule at the surface. No significant results. So we found a much simpler technique, which is based on the fact that our material is very hydrophobic, repulsive for water molecules. The homemade system is like that. It's very simple. We have a light source, a screen, a camera, a magnifying camera, and we deposit water droplet containing our functionalized nanowire on the surface, and we see the contact angle between the droplet and the base, because the contact angle is very sensitive to hydrophobic or hydrophilic nature of the material. And this is, for instance, is the case of droplets which is put on the bare germanium substrate. The contact angles are very convex, let's say. Both in the case of bare germanium substrate without no nanowire. In the case of bare germanium substrate and germanium nanowire with no functionalization, we have more or less the same contact angle that demonstrate that the surface, also containing germanium nanowires, is hydrophilic, attracting the water. On the contrary, when we put our droplet on functionalized substrate containing functionalized germanium nanowire, you see that the contact angle is dramatically changed. This demonstrated that germanium nanowires are really functionalized, because in that case we have a very high hydrophobic surface. So we couldn't see directly, but in this way we could demonstrate that we were able to functionalize our material. So this was just the first step of our preparation, because we should use also different molecules. The basic of the technique is to mount, to attach such a amino terminating group on the surface of the material, and the amino terminating groups will attract the TNT molecule, which will form a weak binding with the molecule, and this will modify the electric field in the vicinity of a nanowire surface, and everything is suitable for preparing a field effect transistor able to detect, and we have demonstrated it, able to detect the presence of very low density of TNT molecule in the air, in the order of 10 to the minus 8 the pressure atmosphere. So the conclusion of my talk that at the end we were able to prepare germanium nanowires. It took some time to get the proper parameter of the germanium nanowire, but at the end we were successful, and we used a gold nanoparticle as a catalyst, and we could determine, we could perform electrical characterization of nanowires, both detached from the substrate, dispersion or carrier substrate, and make a focused ion beam contact. And we found the resistivity of single nanowire in a range of 0.1, 0.2 ohm centimeter, which is a proper value to prepare field effect transistor. And at the end, we were able also to demonstrate functionalization, and the functionalization was demonstrated by contact angle measurement, a very simple technique but very effective. Demonstrated that we were able to mount, to attach our functionalization molecule on the surface of the cell. Okay, this is the conclusion of my talk. Thank you for your attention. This is the project which was supported by the NATO Science for Peace and Security program. So we were not working for the army, we were working for military purpose, we were only working for security, and this was supported, this was the portable sensor for unmanned explosive detection, because I told you that in principle we should mount our sensor on a drone. In that case, you can detect explosive without direct human intervention. Okay. These are trinitol when sampled that are not dangerous. Okay, thank you for your attention. I hope it was useful for you.
Thank you, sir.
You have shown a 111 oriented nanowire, right? 111. Yeah. So which gives you the better result, 111 or 100?
But there is no particular reason of choosing this orientation of the substrate. What is sure is that in any case, the nanowires grow along a 111 direction, in any case. So if we use a 111 oriented substrate, we expect a vertical nanowires. But since you have to detach the nanowire from the substrate, it is not so essential the orientation of the substance. So it was just by chance, not something special about this.
A fantastic talk for the current conflict-ridden world. Landmines that are embedded from the World War II era. So this is regarding the concentration of these TNT molecules, which you might be expected to detect in the neighborhood. So how effective are general gas sensors? I want to know what is the molar concentration of these molecules outside the bomb and as we go along. So that we need to know how close your detectors, the unmanned UAVs should reach near the landmines so that you will be able to detect it without getting false alarms. So can you give us some idea as to what is the vicinity and what is the molecular concentrations near a landmine?
Yes, you are perfectly right in the sense that I must be sincere. It is very difficult to detect landmines in this way. The reason is that I told you about the gas concentration in equilibrium and at a given temperature. If it is your device, explosive device, is put inside a room, you may expect that after some times, it takes in any case several 10 minutes or half an hour in order to reach such an equilibrium, and you must have a very close room, of course. I know that in any case, for instance, dogs are able to detect landmines in such a way because their nose is extremely sensitive, much more sensitive than our device. So in principle, it is possible to use it, but in the open air is extremely difficult. I must be sincere. But our original idea was not to use such a detector to detect landmines, which is a very difficult task, but especially to detect devices, explosive devices, especially improvised explosive devices, which are kept inside rooms. In such case, you may imagine to use drone to enter the room, to the window, to the door, and detect gases, traces of gases in a room. In that case, you may expect that the gas concentration is much higher than in the open air. But in any case, it is surprising that dogs are able to detect TNT and landmines even in the open air. So that means their nose is fantastic. And also, in a conference, there were people showing that also bees are able to detect such landmines. They must be trained. It is difficult to train bees, but in principle they are able to detect because their nose is also very sensitive because they should be able to detect the presence of flowers at kilometers of distance. The method in principle works, but it's not easy to train bees, and the life of the bees is not so long, so it is difficult. That's why it's such a difficult time. So I must be sincere. I do not expect to be able to detect landmines, but the explosive device kept in closed rooms.
And regarding the binding of TNT to the nanowires, so we get this field altered and you get the current. So after a detection, should they be flushed out for reuse, or it's a one-time usage?
No, these are absolutely a critical question. So no, we demonstrated. I have with me some other slides that demonstrated that we were successful, but without using nanowires. I should be sincere. In any case, if you remove the gas, then the conductivity goes back to the original value in a few seconds, 10 seconds. That means the speed of reaction for our system is also much higher than reported in literature, because other devices were proposed to detect explosive molecules, especially the one based on oxide semiconducting materials, such as zinc oxide. The advantage with our system is that in that case, the detector works at a much higher temperature, and you need to heat, and this is not. Some of them are very commercial. If you want to detect, for instance, nitrogen dioxide, you can buy for a few dollars on the market. It is, but needs in any case a high current to be warm, to keep high the temperature.
Thank you. Thank you.
So, I just missed one point. Maybe if you can the thing is, it is a gas sensor, and then TNT is a solid one. You said some connection between the solid to the gas sensing.
Yeah.
I just missed that.
Yeah,
point.
okay. It is also very trivial. It's not so trivial. I told you that you can detect the presence of TNT like any other solid substance by the smell. It's because of physics that says that for any solid at a given temperature in a closed environment, there is an equilibrium between the solid and the molecules in the air. Even for iron, even for rocks, molecules are emitted, and in an equilibrium system, there is a given amount of molecules which are spread into the air. Any solid, also for trinitotoluene. And I showed you that this is a well-known dependence of such molecule content in the air that is also described by a partial pressure of molecule in the air, and the temperature. If you increase the temperature, of course, the content of molecule in the air increases very rapidly, exponentially. So if we heat to 300 degree trinitotoluene, and then you have one molecule have 10 to the 6 molecule of air. And maybe also by your nose you can feel. But room temperature is almost impossible for us to detect. For our dog, it is. But also the dogs need to be trained.
Sir, thank you, sir. And then, is it put in use, sir, with the unmanned explosive
Sorry,
sensor?
it is?
I mean, is it used right now, your device?
The project finished. We arrived at successful results, and then we need the application. Okay, we were not successful in the last part of the project in the sense we said in the project that we should mount on a drone, and the drone should be able to detect. We missed the last part of the project. We had the drone, we made control, we mounted, but we couldn't find a proper way to demonstrate it. At the moment, it is in such a condition. But we had the interest from other companies that are interested. But for the moment, we are waiting for support.
Thank you, sir.
So, it's a very generic question. Is there any kind of side effects for sensors when it goes out to the public? And is there any kinds of precautions the manufacturers intake before you?
Any side effect or what?
In the sense when you when the public uses it, does the public have any kind of side effects for any particular sensors? In the sense, it could be due to radiations or anything as such. Not specifically this sensor, but in general. And is there any precautionary measures that manufacturers undertake before you give it to the public, use it in the public?
But maybe, I'm not sure if I understood your question, but the sensor do not spread into the air. They are attached to the substrate, or there is no possible interaction with public from this point of view. Maybe it's more dangerous trinitotoluene. I know a history that at the beginning, now it is considered a dangerous material, but not because it explodes, because of pollution of the air and in the long time has an interaction with your health. I read an history that during the Second World War, the women were used to fill with trinitotoluene shell bombs, and they were managing the material without any precaution. And the first step was that the skin became yellow, and after some time they had also health problems. This is but because of TNT, not because of the sensor.
Thank you.
A very good afternoon, sir. Welcome to MCC India. I'm Arun, and my topic question is general question. And future of defense sector is going to be unmanned vehicles.
And try to understand that I am not native English speaker, and then maybe you can say it slowly, because otherwise I cannot understand.
Yes.
Sorry?
Future of the world in defense sector is to be an artificial and unmanned. And research on NATO countries is using in defense sector of developing of unmanned aerial vehicle and ICBs, intercontinental ballistic missiles. And what is the efficiency and future of sensors in the field of the defense sectors, and how the efficiency to be achieved? This is my question.
Can you help me? Because
since NATO is using all these unmanned vehicles and other things to detect explosives, he is asking whether this type of sensors will be used for the detection.
yeah, in principle they can be used for this, but I told you at the moment we have not extended our application, but NATO is a kind of research institution that not always applies the research results and make something that can be produced. For us, it's like a European project. A European project is essentially made for fundamental research. In that case, it's something between fundamental and applied research. I'm not sure if I have covered the answer.
Thank you, sir.
Enlightening to hear from you. I would like to ask you a question as to regarding national security. How do you see the evolving of the sensors in the next decade? Like since cybersecurity and all those things are in high, so how do you see the sensors being evolved in the next decade?
So I see the national security, what?
Since now the question is like national security in the national security sector,
Yeah.
how do you see the sensors being incorporated or evolved in the next decade?
I think that this kind of detector are needed. There are already existing detectors. For instance, in the case of critical systems like airport or airborne, they use a different kind of detector, which are based on mass spectrometry, which is a very, very sensitive technique, but the detector is much bigger, but you can keep in the same position and simply continue to sniff and try to detect. Our idea was to prepare a mobile detector, very light, to be used as a drone. I think that still is a need which is not completely accomplished. So I think that our idea can be used for that. But another step is necessary to continue the research and go in the direction of application, to increase the level of application.
Thank you.
Good afternoon, sir. Thank you for the interesting lecture. Sir, my question is very general. Sir, could you explain the interdisciplinary nature of developing sensors? That is, how to integrate physics, material science, and electronics in these kinds of projects?
Can you explain what the integration? No.
Sir, how to integrate physics, material science, and electronics in these kinds of projects? Like, the interdisciplinary nature of these projects?
Yeah, I didn't show you, but we realized the detector, and we used a simple Arduino board that everybody can buy in the shop, simply to detect the resistivity of the material, and it was enough sensitivity to make the detector working. In fact, we realized that this is another story, detector, a sensor based on carbon nanotubes, which was working, and also germanium nanowires, which apparently is even more sensitive than germanium. But to integrate it into a device was a relatively easy task. We provide such a board, Arduino, maybe if you work with electronic Arduino, is a very basic board that you can buy for a few dollars anywhere. We also provided a system with a small pump, which is moving gas and fluxing gas on the sensor. So everything could be constructed with a very limited weight, because our idea was to put in a drone, even a very small drone, this size. So this was not a difficult task for us.
Thank you, sir.
More difficult task that I didn't mention to you is that in which way can you recognize the origin of a smell? This is not an easy question. It's because our brain and our nose, and especially the nose of the dogs, combine many sensors, many different sensors at the same time, and each particular smell is associated with a different answer of different sensors. This is why you can, the way in which you can realize a selective detector, because in our case, many other substances affect the sensor sensitivity. I didn't mention, but we tried with nitrogen dioxide, with acetone, in any case we had a huge response. So to make a proper detector, you need to combine many different detectors. But the original idea was that if you want to detect explosive and you put your sensor in a place in which you expect to have explosive, probably you don't need to be so much selective.
Yes, sir. My name is Nishant, and my question is, before the use of sensors to find TNTs or even dogs, or what is the other method that we have to find TNTs in landmines, or generally the places where you are planning to use sensors now? What was the previously used method that is successful or not?
Yes, many other methods are used for detecting substances, and in particular trinitotoluene. As I told you, the mass spectrometry is extremely sensitive, sensitivity much higher than we obtained. Gas chromatography is also a very sensitive technique. Many people in literature reported the sensor based on oxide semiconducting materials, which are also very sensitive, but in that case they require to work at 200-degree temperature. So that's why they are much more complicated. So method to detect trinitotoluene of explosives are already known since many years. Practically none of the previous methods are suitable to be portable, easily portable, or even mounted on the drones. So methods are many methods are available, but only few of them are really portable and really can be adapted to other. This is the main reason of our proposal. I must say that you are very careful and kind to continue to hear my words compliment. I never noticed so many.
Good afternoon, sir. Myself, Captain from second MSc. My question is, as you said earlier, TNT is a solid material. It is hard to detect it, but we are using the vapor of TNT, which has, there is a diagram that says in its molecule, above it has electron richness, and below it has electron power. So in between there is a electric field, a small amount of electric field. We are using that electric field to detect TNT. When it comes to your project, we are synthesizing nanoparticles.
I cannot hear very well your voice. You need to put your microphone.
Okay. In your project, the nanowires we made, it is made phobic to water phobic to detect the electric field. My question is, how the sensing of that particular molecule is conformed with the water phobic nature. We made the material to water phobic, hydrophobic.
Sorry, I don't catch your question.
I rephrase the question.
Can you?
No, he's asking that if the functionalization is successful, test it using hydrophobic. So using the hydrophobic, the angle of the contact angle. So is that the right method he's asking?
Okay, because we attach a molecule which is highly hydrophobic, and even we couldn't find a method to directly detect the molecule. The final result is that the surface of the nanowires is highly hydrophobic. So we are pretty sure that we were able to attach the hydrophobic molecule on the surface of the nanowire. Is an indirect evidence of successful functionalization.
Yes, sir. We made the nanowires too hydrophobic, but my question is how the detection happens. What's the relation between detecting the particular molecule using hydrophobic nature that we made?
I couldn't catch your question.
The hydrophobic study is to test whether the molecule is embedded in the nanowire. That proves that they have got the molecule, embedded in the nanowire.
By all chemicals, if
the chemical is
embedded, then it will show hydrophobicity.
See, they had germanium-based nanowire. We have to embed a molecule in it in order to detect.
Only if there is a contact, it says that it has been embedded there. So it is a phobic nature will ensure that the functionalized material has been there, detected in the sensor.
Thank you, sir.
Thank you.
Thank you, sir. I now invite Dr. Caroline Victoria, Associate Professor, Executive Committee Member, Physics Alumni Society, to propose the vote of thanks.
Good afternoon to everyone present here, and especially Buongiorno Senate. It's our pleasure and honor to listen to Dr. Claudio Ferrari, Director of Research, the Institute of Materials for Electronics and Magnetics, IMEM, National Research Council, Parma, Italy. Sir, thanks for giving a
giving us an insight into gas sensors used in heterostructure functional material and for detecting explosives like TNT. Thank you, sir. You have made our minds to explode this in this maybe. I'd like to thank you once again for delivering the prestigious 13th KMK Endowment Lecture in MCC. Hope your visit to MCC was meaningful and cherishable. I would like to thank our own, I should say from now on, to Dr. A. Stephen, the head Department of Material Science, University of Madras, for adding yet another high-profile speaker to our list of speakers of KMK Endowment Lecture Series. Of all years of collaboration, maybe this year is special with you, sir. This year, I also like to thank Dr. Balaji, Assistant Professor, Department of Material Science. And I also wish to thank Mr. Ribeiro, our own person. Thank you for your presence, Ribeiro. And I would like to thank our HOD of the Department of Physics, Dr. Samuel Asirvadam, for arranging, initiating, finalizing, planning and whatnot for this lecture. I won't say, sir, this is your last one because you are retiring this year. Because hopefully, as a president of Physics Alumni Society, you will be there with us always in the KMK Endowment Lecture in particular. And I would like to thank the Physics Alumni Society for generously contributing towards this KMK endowment. I thank Dr. N. Lakshminarayanan, President, Physics Alumni Society, and Dr. Sam Paul, and all the executive members and loyal members of Physics Alumni Society for their devotion and interest in the conduct of this endowment lecture. I would like to thank our principal, bursar, and their officers for helping us for various arrangements for this lecture. I would like to thank our faculty for their interest and enthusiasm in conducting the conduct of this lecture, and especially to Dr. Prasanna, Dr. Janet, and Dr. P. Subhashini and Lani, and for the help from Physics Society always. A special thanks to Dr. Joseph Jeremiah for emceeing the program. I wish to thank Dr. Jacob George for helping by all means. He was there with me and HOD sir for all the deliberations and executions. Thanks, Jacob. I would like to thank our dear students for your presence, and especially to the AV team, Jairus, Sham, Matthew, Kaiser of 2nd MSc, and Alan of 1st MSc in particular, and all the volunteers for helping throughout the program. I thank our department choir for their singing and Jacob for helping them. And I also thank the non-teaching staff for their immense support throughout. I wish and hope this lecture would have been a wonderful experience to everyone. If you wish to listen to this lecture again, you can watch the KMK Endowment Lecture Series in our Physics Alumni YouTube channel as well as in our website, PAS, Physics Alumni Society website. It will be uploaded as soon as we finish all the recordings and other things. If God willing, we would again assemble next year for the 14th KMK Endowment Lecture. Thank you.
Herewith, we are signing off the 13th edition of KMK Endowment Lecture. Thank you, one and all.